Okay, define and calculate expected value, variance, and standard deviation. Unsurprisingly, these really long words, so I've used the short version, but that's what they stand for. Just so you know, expected value can also be represented as mu. So that's a Greek letter for it. And standard deviation can be represented by lowercase sigma. Sometimes these will have mu of x, actually that should be a capital, which we'll get to, and sigma of x. So sometimes you'll have subscripts like that if you have multiple variables all at the same time. One thing that I want to point out pretty early on is lowercase x means a specific outcome for the capital X, which is the entire possibility of some random variable. So, for example, if I'm flipping a coin, that would be a capital X or a capital letter. It doesn't have to be X, it could be Y, it can be J, it can be anything you want. But the capital means the entire possibility of events, and then X is just one specific outcome. Okay, so what's an expected value? You can think of an expected value as an average, but that kind of gets a little bit problematic sometimes. So more properly, we can define it like this, at least for discrete variables, but we'll come to continuous later when we get there, which isn't that far away. So capital sigma, so add up all of the values of lowercase x, so the specific outcome. That lowercase I just means the first, the second, the third, the fourth, and you just keep going. So I've got all my specific outcomes multiplied by the probability of those outcomes. And if we wanted to be a little bit more fancy, I'll fix that up slightly. In fact, I'll make this PR. I'll make that capital X equals XI. So that's the probability that the random event actually becomes this specific event. Beautiful. We'll do examples of all of this shortly, but I'll just run through this so that if you do the examples and then later on you just want the short version, we can get going. Variance is a whole bunch of different potential definitions. None of them are particularly nice and intuitive at all. Basically, these give you an idea of how different the results can be. So again, capital sigma, so adding up the value of any specific outcome minus by the mean outcome or minus by the expected value, and then squaring that and multiplying it by the probability that you actually landed on that outcome. So you do that for every outcome and then sum them up. Alternately, you can read it as, this and this actually say the same thing. It's just that's the much more compact way of writing it. And so by having a capital X there, you're implying that you're adding it up across every individual outcome. So these say the same thing, just this is a much shorter version of it. This is a bit more explicit. The other way you can get there, which turns out to be equally valid, which is handy, is if you take the expected value of the square of all of the outcomes and minus the expected value squared. And those are different things. So yeah, this would be if instead of having 1, 2, 3, 4, 5, 6 for a roll of a die, you had 1, 4, 9, 16, so on. And then you ran the expected value off that. Whereas this one is you calculate the expected value and then just square whatever that number happens to be. I'm hoping I got that the right way around. If I don't, that's okay. We'll deal with that in a second anyway. Standard deviation is another way of measuring how much these things vary, hence variance. So it's just a measure of how distributed they are, how spread out they are, and that's just the square root of the variance, is the simple way of saying that. At this point, I'm not going to run through the difference between sample standard deviation and just standard deviation, because we don't have to touch it yet. To be clear, variance and standard deviation should always be greater than, or technically you could be equal to 0 if you had absolutely no variance, but then you don't really have a probability distribution because it's going to land on that one value. So it should always be greater than 0. So in the chance that I've got this backwards, you just take the absolute value and you're fine. So these should always be bigger than 0. Your expected value can be negative. Just depending on what your outcomes are, because if you've got some positive outcomes, some negative outcomes, then it's possible that the average is negative. Or 0 for that matter. Cool, beautiful. Some extra bits. So, the expected value of some variable multiplied and then added by a constant is equal to that multiplier by the expected outcome plus a constant. So that's a whole lot of words. Let's think through what that means after we calculate this expected value. So let's calculate an expected value. This table just represents rolling 1d6. Nice, boring, easy example. So I've got, from back here, I need to add up my outcome rather, multiply by the probability of that happening. Okay, so I've got 1 times 1 on 6 plus 2 times 1 on 6 plus 3 times 1 on 6, and then so on down the line. If these were different probabilities, then each of these would associate to its own probability. But I want to use this because it's a much more familiar scenario. Cool, okay. Pretty conveniently we can take out a 1/6 in this case. So we can add all these up. What do we get? Oops. 21 on 6. Simplify down, divide by 3, 7 on 2, 3.5, whichever one you prefer. Okay, great. So we've got an expected value of 3.5. Notice that 3.5 is not actually a possible outcome. That is very, very common. So don't think that, oh, what's the expected outcome? Well, the expected outcome is a number between 1 and 6 inclusive. Well, yeah, kind of. What this means is not this is what we expect to happen. It's just over infinitely many rolls of this random variable, what would be the average? Well, that would be 3.5, which hopefully intuitively makes a bit of sense. That's all it means. It doesn't mean you're going to roll that or anything like that. It just means that's what you'd expect to average in the long run. Beautiful. So now we can talk about what this means. Imagine for a second that we multiplied all of our outcomes by 5. What would happen to the expected value? Well, all of these are 5 times bigger, so all of these would be 5 times bigger, so this would have to be 5 times bigger. Kind of obvious. Or in other words, if I take a die and roll, and then I multiply whatever the result is by 5, what would I expect over the long run? I just expect everything to be 5 times bigger. So my expected becomes 5 times bigger. So E of AX would be A times E of X, because it doesn't actually change the random part of it, it's just multiplying everything. Similar idea, if I add something to it, so no matter what I roll, I'm going to add 7 at the end. How is that going to affect my expected value? Well, it's not going to affect the randomness of it, it's just going to add 7 at the end. So I can just take the expected and add before, or I could add afterwards, won't make any difference because I'm always going to add 7 regardless. So that's where the reasoning for that comes out. Variance absolutely sucks. So we're going to run through this the manual way. This is going to be very painful for me, hopefully for you. You don't have to do it more than a handful of times in your life. But here we go. So, first thing, XI. So XI is just the outcome for each, well, just going down the list of the outcome. So we've got 1 through 6. All right, 1, 2, 3, 4, 5, 6. Brilliant. XI minus mu. So remember, mu is expected value, same thing. So 1 minus 3.5 would be negative 2.5. Similar story for the rest of it. Plus 0.5, plus 1.5, plus 2.5. Beautiful. Now we want to square each of these. Okay. Which off the top of my head I'm going to forget how to do. 25 is 625, I'm pretty sure. Yep, 625. Where's my text on? Cool. Get rid of that negative, so that's fine. 6.25. 15 is what? 225. Yep. Is 0.25, and then similar story for the rest. At this point, they should all be positive, because if they were negative, they should have gotten squared out. And we don't have any complex. Beautiful. Times this result by the probability that it was going to happen. Well, in our case, everything's 1/6. So 6.25 divided by 6 gives me 1.0416 recurring. 2.25 divided by 6, 0.375. 0.25 divided by 6, 0.0416 recurring. And these will all be the same. 1.0416. Okay, so we've got all that. If we go back to our definition of variance, what have we done? We've got xi minus mu was our first column, so that's inside this bracket. After that, we square the result, that was the second bracket. We multiply it by the probability of landing in that particular outcome, that was multiplying to here. Now we need to sigma that, so we need to add up all these, so we get whatever we get. This plus 0.375 plus 1 point, oh, like that, plus this, yes. Cool. And unless I've fat fingered something, gives me 2.916 recurring. Cool, so therefore that is my variance. Beautiful. Wasn't that a whole lot of fun? No, of course not. This sucks to calculate manually. Conveniently, however, we can do it on a CAS instead, which I'll go through in a second. But for now, just what I want to touch on, variance. Okay, what if we fiddle around with our variable? Alright, well, if we multiplied everything by some constant, that would mean that all of these would have got multiplied, okay? That won't affect mu because mu would have had the exact same multiplier effect, but we square it here, and then we multiply by the probability, which isn't affected by a. So all of these would have copped an a and squared it, so it all would have copped an a squared. We add them all up at the end, so they're all a consistent factor of a squared, so that's why this becomes an a squared. If I add to all of this, well, if I add to all of them, that means e of x would also go up by the same amount. So when I minus it away, I'm going to have b times, xi plus b minus, in brackets, mu plus b. All the b's will end up cancelling. So by the time I get to here, all the b's have disappeared again, and then I'm going to the exact same number. So that b should always just drop off. So that's a nice general rule. Fantastic. Okay. And while we're here, we might as well do the standard deviation, which is a lovely, terrible number. And it commonly will be terrible. 0.078-ish. Cool. Oh. So we get some terrible number. That's very, very, very common. Now, what does that standard deviation mean? Well, if we take something that is at least almost normally distributed, if it's perfectly normally distributed, then it'll end up being very close to this. But for most things, maybe not even most things, but for a surprisingly large number of things, things will be what are called normally distributed. When we get into continuous variables, we'll touch on this further. But for now, that's why I've got asterisks on this. This is a super vague sort of general thing. Doesn't always apply, but it's a pretty good rule of thumb. So the probability of being between two standard deviations below the mean and two standard deviations above the mean, that happens roughly 95% of the time. We'll be a bit more concrete about this later, but for now it's just a good rule of thumb. If you haven't done any of this stats before, if you have done it either with me or in further already, then you'll be familiar with that idea. We're going to take it a bit further, but for now, that's going to be where I leave that. To do this on a CAS, change over to a CAS. Cool, so open up a spreadsheet, so that's the second one from the bottom left. We're going to end up with A, B, and C, and so on, so on, so on, and 1, 2, 3 down the side. We're going to leave the equals part empty, and we're going to fill in these values. So if we fill them in 1, 2, 3, 4, 5, 6, just like we've got up here, and stop, and then go up and put the probabilities next to them. In this case, it'll be 1/6 for everything, but if they were different values, obviously you pair. If 1 was 1/3 and 2 was, I don't know, 1/8 or something, then this would be 2/3, this one would be 1/8, so on, so on, so on. So you fill in your grid. From there, we're going to go menu. From there, we're going to go statistics, which is the fourth on the options. From there, we go stat calculate, or statistics calculation, I forget the full words. Then first option will be one variable analysis, I think it's got in there. Then after that, it'll bring up a simple window that says number of lists. We're just going to put 1. Even though it looks like we've got 2, this is really one set of data, so it's going to be called one list. Cool. After that, it'll bring up another window where it'll say x1 list. So this is talking about, okay, what is your random variable, hence why it's got the capital X. The 1 is just saying we've only got one list, doesn't have more. Cool. It should default to having a, lowercase a, and then open hard bracket, close hard bracket. It may or may not, depending on where you are on your screen when you do it. So make sure that this a is whatever you put your x outcomes in. Similar story for the frequency. It should default to b, but that should line up with whatever you put your probabilities in. So this frequency reads more as a probability for this scenario. There'll be a bunch of other things. Scroll straight past. We want the results column. Again, that should default to C, but depending on where you were, it might go to somewhere else. Or for some reason, you might have something else already in C, so you don't want it to overwrite. It will start writing from whichever letter you put in there. So I put it in C. In this case, it'll take up C and D because it's got two columns of output. From there, we get a whole lot of things. It'll come up with a title. It'll come up with an X bar, which means the average, which in this case will also be equal to the expected value. It will bring sigma x, which happens to be 3.5, and a bunch of other things. It'll have Sx and sigma x. So sigma x is our population standard deviation, which we'll clarify later. Sx in this particular case happens to be undefined, which is nice. Those will be very, very close to each other. Well, the vast majority of the time they'll be very close to each other. Right now we're only looking at this guy, which is 1.70782, great, that matches. And then it'll give you other stats underneath that, which if you've done further, you're a bit more familiar with. So that's that, that's 13D. Most of this is, once you get a handle of it, it's really straightforward. The only annoying thing is if it asks you to manually calculate variance from just a set of data. Commonly they'll give you pieces of it, so they might give you, here's E of x, here's E of x squared, tell me what the variance is, in which case you just square the first one and then you're good to go, take the difference. Beautiful, so that's 13D. If you've got any troubles at all, email me, otherwise see you later.